Hello everyone. I can see there's a lot of people online. Free. Anyway, how is the volume? And hello everyone. Okay, I see the volume is there's almost a lot of people. Okay, online. So today I'm going with a different approach for this. I'm trying to explain the Q-learning paper. This paper was written in 1989 by Watkins. It's one of these algorithms that affected a lot of things that came after it. It's a really easy read. Don't be too scared of the math in here. If you just pay a little bit of attention in here, you will be able to power through this 14 pages document. If the proofs are giving you a hard time, you can skip through. You can skip the proof and just power through this little document. It's a really nice read, actually. And before I go into any of the math in here or how this works, I will introduce some basic concepts about reinforcement learning. So I will just go over some concepts in machine learning quickly. A couple of concepts here. Just want to make sure this is visible to the camera. Okay. So we have two main branches: supervised learning and unsupervised learning. That people categorize most of machine learning into. Some people include reinforcement learning in unsupervised learning or put it somewhere in the middle, but it should be a branch on its own. Anyway, so with supervised learning, let's talk about let's take an example of classification. So I have a bunch of pictures in here. Some of them are letter A and some of them are letter B. These pictures can be cats and dogs or anything else. We have a model in here. This model will take an input of A and it will try to predict what's the output of that. It will try to predict whether it's A or B. So if it predicted it correctly, if it gave us an A, I will do something like a back propagation in here to reinforce the gradients inside this model to give it basically a positive reinforcement here. If it predicted it incorrectly, it gave me a B in here instead of an A. I will try to adjust basically my parameters in here. Depending on the algorithm, the parameters are different, but that's the basic concept of what supervised learning is. You have some input, you try to predict some output, you calculate the error between your predicted output and your expected output and use that error to fix your model. So that's supervised learning. Unsupervised learning, I will take an example of classification. Let's say I have a bunch of things in here. Let's use this color. Let's say I have a bunch of points in here and some other points in here. With unsupervised learning, what I'm trying to do is with the classification, I'm trying to create some rule to say this is one cluster and this is the second cluster. So I'm trying to separate my points without knowing their class. So this is unsupervised learning. There is no supervisor telling this what is the correct answer. These points are fit to the model without their classes. And here I clearly have classes blue dots and pink dots, but in practice we don't actually tell it what the class is. So the algorithm will try to do something like this. It will try to do, this is one class and this is a second class. Or with some other algorithms, it will try to draw a line between them. Or some other way of separating these two. So if I give it some unknown point, let's say I give it a point in here, it will be able to say this new point that was not part of my training belongs to this set. If I give it a second point that was in here, for example, it will say this point belongs to this set. So this is unsupervised learning. So these are the main two categories of machine learning, and supervised learning and unsupervised learning. What I want to do now is try and explain what reinforcement learning is. So with reinforcement learning, I don't have any of that. I don't know what's the answer also. So it's an iterative process where I have a state. Let's call it an S. And I have an environment. There's the letter E in here. And I have an agent. That's taking a current state. So let's put the actually that's not really the best way to draw this. Let me do it in a different way. I'll put my state in here and I will put my environment in here, and I have an agent. Basically I have an agent, call my agent A. This agent is, let's to visualize this or to understand this, let's consider this as a robot. So this robot receives a state. This state can be anything. In a context of a robot that wants to learn with how to do a specific task, the state is whatever the sensors of that robot are at a specific point. It's reading some temperature, maybe it's measuring some things with ultrasonic sensors or anything else. So some state is coming into our agent. The agent is trying to pick one of several actions. So in here the agent will try to perform a specific action. So in here I have an action. Okay, sorry, I'm writing sideways, so it's really weird for me to write this way. Anyway, the agent is trying to perform some action based on what the state is. The environment will feed back some kind of a reward back to the agent, and produce a new state. So let's take an example of this to make this more concrete. Let's say I have a production line in here, okay? And I have a bunch of boxes coming through the production line. And I have a robot in here. Let's do some robot in here. It has a claw. And it has I don't know, and this robot can measure also the temperature. And here it's measuring the temperature of each one of these boxes. The robot arm will be affected if the temperature of the box is too high, for example. It's supposed to pick boxes which are not too hot. So it will try to measure the temperature and it will try to pick up the box. And if the temperature is too high, the robot will have some kind of a damage. So it has a second sensor in here, or yeah, it has a second sensor that's reading if there is any damage in the claw of that robot. So first box comes, the robot in the beginning will measure the temperature of this box and will decide this box is the right temperature. It will try to pick it up. There is no damage in the sensor. I will feed back, I will give it a positive reward to say this was the correct action. Second box comes in, the temperature is too high, it decides not to touch it. There is no damage in here. I will give it again positive reward. Let's say a box comes in and the temperature is too high, but the policy in the robot tells the robot to go and touch the box. Some damage happens to the robot. I will feed back some negative reward here. I will punish basically the robot for damaging itself. So this is a simple example of how reinforcement learning works. And this is actually represented in a mathematical way. The mathematical way of representing this would look something like this. Let's say these are the actions. So this is my policy. Let's call my policy pi. Pi, just a bit bolder, so it's clear. So I have two states. These are my states. I have cold state and I have hot state. And I have actions in here. These are my actions. Action yes, or yes, which means pick up the box, and no, don't pick up the box. So in the beginning, I will start by initializing my policy by something in the middle, 0.5, 0.5, 0.5, 0.5. The robot now, let's go back to our picture of the awesome robot in here in the production line. The robot in the beginning reads a temperature and decides this temperature is hot. It will go and see what should I do with that. It knows the temperature is hot now, and it will try to do one of the two actions. It can do two actions only. Pick up the box, don't pick up the box. But because they are identical in value as far as this policy is concerned, it will try to do either one of them randomly. So let's say it decided to do the pick up the box when the box was hot. What will happen is I will feed the robot some negative reward. So let's say I will give it a -1 because it chose this one. I will take now this -1 and I will affect my policy with that. So what I will do is I will multiply this -1, or I will basically add this -1 to my policy, but with some gamma, with some learning rate. So I will not completely make this, I will not deduct from this -1. I will deduct a very small number. So I will multiply this -1 by some number, which is my learning rate. Let's say my learning rate is 0.1, for example. I will multiply this reward by some learning rate, and I will, alpha actually is the learning rate. I will multiply my reward by this alpha, and I will add this reward, which is basically a punishment in here. -1 times 0.1 equals -0.1. and I will add that reward to this box in my policy. So it will be 0.4. Let's say a second hot box comes in to this production line. The sensor reads hot, the robot goes and checks the policy. If it picks up the policy, it thinks the reward should be 0.4. If it doesn't pick it up, the reward is 0.5. So it will decide not to pick up the box. If it doesn't pick up the box, I will give it a reward of 1, because this is the desired action that I wanted it to do. So 1 times my learning rate of 0.1 equals 0.1. I will add this 0.1 in here. Let me do that in blue. 0.6. You can see how this can eventually make this policy converge to the optimal policy for the robot. This will eventually converge to 1.0. This will eventually converge to 0.0. And this will eventually converge to 0.0, and this will converge to 1.0. So as this robot learns using this reinforcement learning method, it will learn the optimal policy for doing this task. So let's try to write this in some mathematical notation so we can get the fear of writing these things in mathematical notation. This formula in here actually is the value function of in Q-learning. So let's write this formula and try to understand what does it mean. So V for value, this is our value function. It's trying to figure out what's the value of doing an action. So what's the expected value of doing an action? So value in regards to pi, in regards to this policy pi, given x. X in here means our state. So what is the input, whether it's cold or hot? Given x equals the reward given the policy, given this policy, where the policy receives the state x. Okay? This was a very simplified version of the example. In real life, we want to get, sometimes there is more to the formula than just this, which is taking into consideration some previous values. Let's try a second example, then we'll finish this formula. I will take a second example now. This example is, I have some maze in here. This maze is maybe something like 3 by 4, and our agent, let's draw a stick figure in here. This is our robot. And our robot wants to get to, I don't know, some pizza slice. Slice of pizza in here. The goal of this robot is to get to the slice of pizza. I know my drawing skills are amazing, so just you need anyone to illustrate things for you, you can hire me. Anyway, and I want to get to my pizza using the least amount of time to get to my pizza because my agent is actually hungry. Or so I could, my actions are either to go up or right or down or left. And here, two of the actions are not possible. I cannot go left, I cannot go down. I can either go up or right. My state is in this box and the pizza is in this box. So my state is both my location and the location of the pizza. So it will learn, okay, let's go up. Then let's say it decided randomly to go up again. Then it decided to go right. It decided to go down. And decided to go down. Then right. Then up. And it decided to go left. And it just kept roaming around for like 50 steps inside this maze until it got to the pizza. This is obviously not the optimal policy. So I want to give it a reward for eventually making it to the pizza when it was in this box, for going up, for doing the action of going up to the pizza. But I want also to give it some backfeed to few of the previous actions. So let's say it was here, and instead of going left, it actually went up. Then it went up again to the pizza. So I want also to let it know that this previous action was correct, and the previous action was correct, but less correct and less correct and less correct. So all the previous actions that led it to getting to the pizza are gonna get some reward in my policy. So eventually I get to the pizza. Now I know whenever I'm in this box and the pizza is next to me, that one will have a very clear policy to tell it go up to the pizza. And if I'm 2 steps away from the pizza, it will learn go up, then up again. So next time it tries this policy, it will only do 20 steps maybe before it gets to this box. Then it will decide, oh, I'm in this box, I already have some policy that tells me go up, then up again. So when it got to this box, it used to be here, then it used to be here before that. This will get some high reward now for going right, and this will get some high reward for going down. So eventually it will start finding shorter and shorter and shorter paths to getting to the pizza by feeding not only the last step with a positive reward, but previous steps that led to this last step, getting to the pizza. Okay, so few hundred iterations later, it will find out that I can go either here directly, or I can go here directly, or some short path of getting directly to the pizza. So now let's look into how we can encode this last part into our formula in here. The rest of the formula says the value function given a state x, giving our position. So our state is where are we in this map and where is the pizza in the map. Okay, so this is our x now, it's our location, and where is the pizza. Will give you a reward given the policy that we're using. So let's create some policy in here, which is a table of which action to do based on where are you and where is the pizza. Go right, go left, and we're deciding which policy, which action to take based on our state. Add to this some residual thing, which is not only the reward of your current state, not only the reward that you think you're going to get from your current state, add to that gamma, which is some number between 0 and 1. And this number is the number that propagates the feedback. How much do you want to give reward to previous steps that led you to this last step. This is gamma times the sum of a bunch of my previous states. So gamma, I'm giving it, I'm adding to the value of my current state the current reward that I will get if I do this, the reward I will get on my current state plus the my previous steps. So I will add to it plus gamma, the sigma of the probability of x and y. We'll expand this in a bit of terms in a second. Of given our current policy of x times the value function, giving our current policy function, our policy pi of our previous steps, our previous states. So our function becomes our value function. How much value are we gonna get from our current state is equal to our current state, our current how much reward are we gonna get from our current state. Let's say we are still here, plus how much do we think we're gonna get in our few next steps to get to the pizza. So let's say I'm in here, and what's my current value? My current value is, if I will check, my best policy is telling me to go right. But that's not all, because I also have some reward if I go up. So if I go up, I will get some reward, then some reward, then some reward, then some reward. But I can calculate how much I'm gonna get for going up, how much reward I'm gonna get for going up in here, and how much reward I'm gonna get. What's our best action once I'm in here? Our best action once I'm in here is telling me to go right. Then how much reward I'm gonna get for going here? It's telling me to go right with some reward. Then once I'm in here, it's telling me to go up. So I can actually estimate how much reward I'm gonna get in the future if I go up, not only for the very next step, but for all future steps. And in here, I can also check what's my current reward if I go right, plus the best plus my reward for all future steps until I get to the pizza. So I can clearly see if I'm in here, going up and going right are giving me roughly the same reward, but going left is giving me less reward. Let's say I'm in here. If I go right or up, I'm gonna get roughly the same reward because it's only 3 steps away from the pizza. But if I go left or down, I'm gonna get less reward. Because if I go down, there is still a path to get to the pizza, but there are way too many steps in here to get to the pizza. So because I have a gamma in here, that's basically reducing the value of future rewards. It's reducing the value that I will receive for future rewards. I will end up choosing the optimal action. So this is a very visual way of understanding Q-learning. I will try to make more concrete examples tomorrow, and we will start building the code for this. we will write the code for this in few steps. So we're going to be building tomorrow, we're going to be building in Golang from scratch an environment, and we're going to be building an agent. This environment can be anything, that any problem that you're trying to solve. Let's say you're trying to build a robot that vacuums your room, for example, like a Roomba. Your environment is gonna be whatever is inside your room, and your agent is your Roomba. So you can actually build that model for training your agent to clean your room or vacuum your room using this cycle. But the environment we're going to be building tomorrow is based on stocks. So it will have some stock price that fluctuates, and our agent will try to find what's the best action to do, whether to hold, buy, or sell, based on what's the current state of the stock market. So it will decide whether it should buy, sell, or hold based on the state of the stock market. That's that part we will start building tomorrow. We will mostly focus tomorrow on the environment, and we will build a random agent eventually that just does random actions, so we can get to eventually build Q learning algorithm into our agent. That's all what I have for you guys today. Thank you for tolerating my new approach, and I hope that was interesting for you guys. Anyway, thank you for getting bored with me today, and I will see you tomorrow.